Welcome to a probabilistic approach to medium-range natural gas demand forecasting. My name is Eelisa, a data scientist here at Marquette Energy Analytics, and today I'll be introducing you to some core probability concepts and showcasing how MEA's medium-term forecasting tool, MCAS Planner, utilizes these concepts to help utilities like yours make smarter, data-driven decisions. And here's our agenda for the day. As mentioned, we'll be leveraging MEA's medium-term forecasting product, MCAS Planner, to demonstrate how we apply each of these concepts that we'll be covering. MCAS Planner helps generate forward-looking monthly, winter, and annual load forecasts to support utilities in optimizing energy supply planning, mitigating risk, and making informed operational decisions. We'll begin with the basics and gradually introduce more complexity as we move forward. Throughout the presentation, I'll highlight how these concepts translate into actionable forecasting insights. The goal here is to present ideas in a clear, non-technical way, ensuring that everyone walks away with a better understanding of these concepts and how they're applied in MCAS Planner. We're going to begin by looking at a load duration curve for one of MEA's demo areas. This visualization provides a comprehensive look at how daily load fluctuated over a given period of time, in this case, a single winter. We can interpret this graph by looking to the y-axis on the side to see specific daily load values, and then we can look on the x-axis on the bottom to see the number of days that reached or exceeded each of those y-axis load values. The points on the far left of the curve show the few days with the highest load or highest Y values during the winter period. As we move to the right, the points along the curve drop in Y value, showing that most winter days had lower demand. The area under the curve represents the total recorded load volume associated with this given period. Historical load duration curves like this one are very useful when trying to understand what has already happened. That is to say, how many days were associated with specific load values in a historical period. While this provides some great insight into the past, curves like this one are somewhat limited in our ability to predict the future. To achieve that predictive power and generate more reliable insights into potential future scenarios, we'll need to apply some probability concepts and methods. This is where MCAS Planner truly shines. Instead of generating load duration curves representing the past, it projects load forecasts into future scenarios. For example, take this cold 1 in 30 load duration curve for the same area in the previous slide. This curve illustrates the forecasted loads that MCAS Planner predicts would occur under cold 1 in 30 weather conditions. And what we really have here is our end goal for this presentation as a whole. In other words, this is what we're going to be building step by step in the following slides. And while Planner can predict load within various 1 in n weather conditions, including average conditions, we're going to focus on 1 in 30, which is a popular planning metric for many utilities. So, how does MCAS Planner get from historical load information to predictive curves like this? Let's start answering that question by exploring some core probability concepts. To start us off, let's first build a solid foundation in probability theory. Let's begin with some simple definitions for probability theory itself and the concept of a probability. Probability theory is the mathematical study of how likely events are to occur. It quantifies uncertainty or chance. A probability is a measure of uncertainty with a value between 0 and 1, where 0 means an event is impossible and 1 means the event is certain. For example, when rolling a fair six-sided die, each face has an equal chance of landing face up. The probability of rolling a -1 is 0 or impossible since a six-sided die has no -1 face. Meanwhile, the probability of rolling a number between 1 and 6 inclusive is 1, or certain. Understanding these probability fundamentals is key to understanding how MCAS Planner applies statistical modeling to generate realistic future load scenarios. Let's explore further. Extending our dice example, we can represent the likelihood of any given event by dividing the number of target outcomes by the total number of possible outcomes. For example, the probability of rolling a 2 on a single six-sided die is 1/6, because only one of the six faces has a value of 2. Similarly, the probability of rolling an even number, a 2, a 4, or a 6, is 3/6, or equivalently 1/2, since 3 of the 6 faces display even values, and this can also be said as half of the possible face values are even. The last two examples on this slide illustrate impossible and certain scenarios. Since no face has a value of -1, the probability of rolling a -1 is 0, and meanwhile, because all 6 faces display a value between 1 and 6 inclusive, the probability of rolling a number within this range is 6/6, or 1, an outcome that is absolutely certain. At this point, we've covered the fundamental concepts of probability theory and probabilities. But as you might have guessed, forecasting energy load is far more complex than rolling a single die. To approach the required level of complexity that such load forecasting requires, we're going to need to introduce a couple more sophisticated probability concepts. Now that we've covered probability fundamentals, let's take things up a notch. The next step? Probability distributions. These are key to getting big picture views of possible outcomes and ensuring more accurate load forecast. We can define a probability distribution as a way of representing the likelihood of all possible outcomes for a given scenario. To illustrate its importance, let's build on our single die example a bit by adding a second die. This will help us better appreciate how probability distributions work. With 2 dice, we now have 36 possible outcomes, and we get this number because each die has 6 faces, and each face of the first die compare with any of the 6 faces of the second die. That gives us 6 times 6 equals 36 total combinations. Now let's say we're interested in finding the probability of a specific outcome using these 2 dice. For example, let's explore the scenario where we want to know the likelihood of rolling these dice and having their face values sum to 8. To determine under which conditions this can happen, we can calculate all the possible dice combinations that result in that sum, which we can see here are these 5 combinations shown in the middle of the slide. Next, we count these combinations and divide by 36 to find our target probability, since there are 36 possible outcomes when rolling 2 dice. This gives us a probability of about 0.139, or a 13.9% chance that a single roll of 2 dice will produce a sum of 8. Now, to continue our journey toward the complexities of predictive load forecasting, let's take things up another notch. Let's suppose we want to add another die for a total of 3 dice, and now we want to calculate the likelihood of rolling a sum of 13 with these 3 dice. In this new scenario, we can calculate the total possible outcomes for rolling 3 dice as 6 cubed, or 216 possible outcomes. This number is a result of multiplying 6 by itself 3 times, reflecting the 6 possible face values for each of the 3 dice. Right away, you can see that this is an exponentially larger set of possibilities compared to our 2 dice scenario. The task of identifying all the combinations of face values that sum to 13 also becomes much more complex, to the point that, at least for me, it's not something I'd want to work out by hand. Now we're faced with a challenge. The complexity of the problem has grown to the point where using pen and paper is no longer a feasible option. But this is actually a perfect opportunity to introduce the application and value of a probability distribution. To recap our definition from a few slides ago, a probability distribution represents the likelihood of all possible outcomes. In this slide, we're using a visualization called a histogram to represent the distribution for our 13 and 3 dice problem. A histogram displays data in bins or intervals along the x-axis, with the height of each bin indicating the frequency or count of data points within that bin. This histogram was generated using basic graphing software, saving me some ink, a napkin, and maybe even some Tylenol compared to my attempting this by hand. If we look to the right side of the histogram, we've highlighted in red the expected likelihood of rolling a total of 13 with 3 dice. This turns out to be 21 cases out of 216 possible outcomes, or about 10%. Now, you might have noticed a smooth curve wrapping around the bins of the graph, hugging the frequency values of each summed outcome. Technically, the smoothed curve represents a different kind of plot from a standard histogram, which would only show the bars. But I'm including it here to introduce our next useful concept, the normal probability distribution. On this slide, we see a single normal distribution based on some dummy data ranging in value from -5 to 5. You can see here that our curve has a bell shape to it, and it represents its data symmetrically around a central value, in this case 0. Most of its values cluster near the middle, and as we move outward, values become less frequent. On the x-axis, we represent specific values of x, just like in our histogram. But on the y-axis, instead of counts, we can now measure density, how tightly data points are grouped around a given value. Here, we can see multiple normal distributions. These distributions are useful because we can fully describe them using just two numbers, the mean, which tells us the center, and the standard deviation, which determines how spread out the values are. In this example, each curve has the same mean, which is 0, but different standard deviations. Although they vary in height and spread, they all share the same fundamental bell shape. One important thing to note is that while each curve helps us understand how data is distributed in terms of density, it does not directly represent probability for an exact x value. We'll explore this idea further in later slides, but for now, just keep in mind that density is not the same as probability. So, now we've seen how normal distributions can be useful for modeling certain scenarios like rolling dice. However, when we move to real-world applications, such as representing energy load over time, the limitations of assuming a normal distribution become more apparent. To illustrate this point, here we have a histogram and smoothed distribution curve representing the actual daily loads of one of MEA's demo areas over a single winter. I'll be referring to winter loads throughout this presentation, but you can keep in mind that MCAS Planner is able to provide individual month and annual forecasts as well. As we can see, this distribution clearly lacks the predictable spread and symmetry that are characteristic of a normal distribution. If we tried to fit a normal distribution to these actual loads, the resulting curve would be highly inaccurate. And to illustrate this point even further, we can see that when we include even more years of historical load data, records of daily winter loads consistently deviate from a normal distribution shape. This lack of normality, which is common in energy load patterns, makes it clear that forecasting methods that rely on normal distribution assumptions may not be the best fit for analyzing and predicting load. This brings us to the next level of complexity we need to account for when generating predictive load duration curves like those found in MCAS Planner. First, we're going to delve into a technique called kernel density estimation, or KDE. Kernel density estimation is a probabilistic technique that estimates a dataset's probability distribution by incorporating information from each individual data point. This approach allows MCAS Planner to better align with the actual load trends rather than relying on rigid statistical models, such as those that assume a normal distribution for an entire dataset. In our plot to the right, the red curves represent individual kernel functions centered at each sample data point. These kernels contribute to the overall estimate, with their combined influence determining the shape of the final blue curve. Areas with higher concentration of red curves correspond to higher peaks in the blue KDE curve, indicating where data points are more densely packed. Now, you may notice that the shape of each kernel appears familiar. That's because, in this case, we specifically used normal distributions as our kernel function. Each sample data point is assigned its own small normal distribution, and KDE works by summing these overlapping distributions to create a smooth, continuous estimate. Instead of forcing the entire dataset into a single normal distribution, KDE leverages multiple normal distributions at a local level to better capture the natural variability in the data. While our previous slide featured an example estimation, this is how MCAS Planner could generate its own kernel density estimation, or KDE, using load data from our demo area. This is a simplified version of the actual MCAS Planner process, but it effectively demonstrates the core concept. It's worth noting that the historical data used to create MCAS Planner KDEs undergoes some additional analysis and refinement, something we'd be happy to discuss in future presentations or summarize in the comments. Once that pre-processing is complete, we apply kernel density estimation to translate load patterns from multiple winters into a single real-world model, one that is nearly ready to provide meaningful insights into future behavior. However, as we discussed earlier, a distribution curve alone doesn't directly indicate the likelihood of a specific load value occurring under certain conditions. Instead, it represents how densely past data points cluster around different x values. To move closer to our goal of actionable forecasting and a predictive load duration curve, we need to reframe this information into a more interpretable probabilistic format. Which brings us to the final concept in our Probabilities Foundation toolbox. Cumulative distribution functions. A cumulative distribution function, or CDF, is a mathematical tool that quantifies the probability that a randomly selected value from a given distribution, such as one for daily load, will be less than or equal to a specific value. On the left, we see the plot of the four normal distributions from our earlier slide, and on the right, we can see here these same distributions transformed by a CDF. Along the left side of the graph, moving vertically, the CDF's y-axis starts at 0 from the bottom and extends to 1. The 0 here represents a 0% probability, and the 1 represents a 100% probability. At the smallest x values, probabilities are very low, meaning that it is very unlikely that a randomly selected value will be less than or equal to those x values. As x values increase from left to right, however, probabilities rise. This reflects the increasing likelihood that a randomly selected data point will be less than or equal to each of the rest of the distribution values. When we reach the very rightmost arm of the curve at those very high x values, it becomes nearly certain that a selected distribution value will be equal to or less than that specific higher x value. The concept of a cumulative distribution function is particularly useful for interpreting complex probability distributions. It's exactly how MCAS Planner transforms kernel density estimates into more meaningful insights. And here we see the same transformation applied to our example MCAS Planner-like kernel density estimate. On the left, we have the original estimate where we summed past winters as our kernels. And then on the right, we have the cumulative distribution function, which represents the likelihood that a given load will be less than or equal to the load value shown on the x-axis. With this CDF transformation, we now have a clearer framework to interpret our density model featured in the graph to the left in terms of likelihoods featured on the graph to the right. So if you recall, our targeted forecasted load duration curve from the very beginning of this presentation represented a 1 in 30 weather condition. To hone in on the relevant data, we can sample the CDF at specific points of interest. So for predicting 1 in 30 highest demand loads, also known as cold 1 in 30, we can start at the highest demand levels all the way to the right of the curve and move along the curve to the left until only 1 in 30 or 3.3% of data points remain above our sample point. This is represented by the rightmost blue point and shows us that only 3.3% of our daily loads are likely to be higher than our cold 1 in 30 sample. Alternatively, for predicting 1 in 30 lowest demands, also known as warm 1 in 30, we can sample the CDF at the opposite end, where only 3.3% of data points fall below our sample point. So you can see that by strategically sampling CDF points in this way, we can start translating our probability model into more interpretable insights. Now, to complete the picture, we can take these probabilistic load values from our cumulative distribution function on the right and map them back onto our kernel density estimate on the left. This helps us visualize in another way how our sampled probabilities correspond to real-world demand scenarios. And with this, we now have the key probabilistic data point needed to forecast our 1 in 30 cold load duration curve, specifically the probabilistic total load for our 1 in 30 cold condition. And without further ado, here is the product of all our hard work translated back into a simplified MCAS planner cold 1 in 30 load duration curve. Our cold 1 in 30 load value that we saw in the previous slide, roughly 135 million units or decatherms, is here represented as the total area underneath this curve, and the shape of the curve itself has been adjusted to match historical patterns for this area. This helps us make sure our forecasts are accurately aligned with the area's most recent weather and load trends. And with this, we have finally reached our goal, a predictive load duration curve. Before concluding, I'd like to take some time to preview a more fully featured example of what a predictive load duration curve looks like in our MCAS Planner product. While this example uses a demo area's data, we'd be happy to set you up with insights tailored to one or more of your area's data. As you can see, MCAS Planner allows for side-by-side comparisons of warm and cold, forecasted weather, and average conditions scenarios. Additionally, Planner includes several powerful tools, such as a load value slider, which you can see on the left, which enables users to easily compare reference loads with scenario forecasts, a summary statement near the bottom to highlight key insights, and a handful of additional features not shown here to support more informed decision making. And with that, we have officially completed our probabilistic approach to medium-range natural gas demand forecasting. I hope you've enjoyed this presentation and are walking away with not just a deeper appreciation for some of the key probabilistic concepts, but also a clearer understanding of how these concepts apply to MCAS Planner's scenario-based forecasting. Thank you so much for your time and attention. If you're interested in setting up a planner demo, please reach out to our sales team via the email address on your screen.